Hello, Paul Russo here on a sort of dreary Atlanta day to talk to you a little bit about light scattering. And we are going to start with this picture of our alignment target. And what's going on here, you can see green light. So this is with green laser light illuminating something. And the something that's being illuminated is actually a pin. The light actually hits a little pin, and that's used to make sure it's going over the center of the apparatus. But what you see off to the side here are these diffraction bands. And this is a good chance to illustrate one of the fundamental things about light scattering, which is that it is an inverse space method. The pin is aligned vertically, and that is why these scattering pattern or the diffraction pattern extends to the left or to the right horizontally. And the other thing is that if we were to replace the pin that we have now with a thinner pin, these vertical stripes that you see here would get farther out. And if we were to replace it with a fatter pin, they would collapse even closer to the center. So this business about being an inverse scattering method is important. Probably easier to understand if I tell you what's not an inverse method, and that would be any form of microscopy. That's a real space method. So scattering and microscopy are complementary pairs. Scattering is in inverse space, microscopy is in real space. We'll talk more about this. All right, so this presentation is sort of centered on, in a way, your reference for this would be these two articles that we wrote about a year ago, so they're pretty current. And between the authors on this paper, there's got to be on the order of 60, 70 years of experience in looking at scattering problems. So it's basically what we know and could fit into the article. The editors were very generous to give us a lot of space, but that means they are kind of long articles, but they're organized for the beginner first. So each article has a section that's kind of for beginners, and then it gets more detailed. So why we study scattering is for all the reasons that you see here. It applies in an incredibly large number of things. Interstellar dust scatters, clouds scatter. So there's all sorts of people. So our motivation is that we have just an incredible number of things that we can understand. Also, light scattering works when image fails. It has fewer anomalies and less user prejudice than microscopy. It is still, though, not nearly the detailed view. Okay, so the one thing I want you to understand straight away is where light scattering fits into the general picture of things here. And it is one of the, it's actually surprisingly a kind of a thermodynamic method. It's not going to seem that way for a little while yet. It'll look like we're, just looking at particles and so forth. Most of the things that you study are actually approachable from at least two directions. And in light scattering, it would be sort of a particle-based view of the process and a thermodynamic-based view of the process. But other thermodynamic methods include osmometry. And you think about what's in an osmometer. If I put a semi-permeable membrane right in the middle of a solution, to separate two chambers, on the left chamber there would be no polymers, so it's just solvent over here. And on the right chamber, there'll be some polymers. But in fact, their fluctuation exhibits little local concentration fluctuations. Well, averaged over the area of the membrane, those local concentration fluctuations don't matter much. And so you can just treat all that osmometry can see is the average concentration. But nevertheless, the method does work by creating a sort of step gradient in concentration. And whenever you have a gradient in concentration, it turns out from polymer solution thermodynamics or any solution thermodynamics that you can actually then get a handle on first the chemical potential and then the molecular weight. And basically all the things that go on when you have gradients here are really things that you would expect effectively from the ideal gas law. Another way on the right here of creating gradient and concentration is to spin the sample. If you spin a sample in a centrifuge very hard, the sample will collect near the bottom. So down here on the right side of this is meant to indicate the bottom of the cell. And as we get towards the bottom, the concentration goes up. And it turns out we can analyze this kind of a concentration gradient in another very powerful method. And light scattering, what it does is it takes advantage of these natural fluctuations that osmometry can't see. Just because osmometry can't see them doesn't mean they can't be seen. Light scattering sees them. And we could try to represent this concentration fluctuations with position and sample as a Fourier sum of various terms. And the light scattering method automatically picks out a particular Fourier component of this concentration fluctuations to study. Okay, it's kind of amazing. So all these methods, all these thermodynamic methods, lead to absolute molecular weights. Okay, so we'll come back to this. Here's a little bit about what I'm going to tell you. We'll talk a little bit about what it's like to see in inverse space. We'll talk about why we might want to do that. I guess we already did that. And we'll talk a little bit about how. We'll talk a little about when there is not scattering. This is actually very illustrative of what goes on. To think of what would a system be like that did not scatter. Then we'll talk about static scattering from atoms to macromolecules. Maybe we'll do a little bit of thermodynamics. We'll just see. Maybe in a separate lecture, we'll talk about dynamic scattering and how it's used for particle sizing. It's a very fast method. We'll talk about small angle methods, both X-rays, small angle X-ray scattering, and neutrons, small angle neutron scattering. And maybe we'll see a few applications here and there. Okay, sometimes we'll see famous people in the scattering field. This is Henri Benoit, a French gentleman who was very instrumental, literally, in establishing scattering as a method. Okay, so let's start with not with scattering, but with a microscope. Okay, so here we have a light source, and actually this is sort of a simplification. That's why it says minus the illumination system. There's already a lot going on here before you illuminate the sample. Sample is held here in the object plane. It's this little arrow is what the sample is, and we're going to try to. I'm going to turn my phone off here, if you'll excuse me. Okay, so what we're going to do is we're going to see how light emanating from a point on that arrow works its way through kind of a complicated series of things and winds up magnified. See, the arrow started this big and it winds up that big. And it winds up on an image plane, typically a camera, but in the old days, a piece of film. So this now would be like a CCD detector over there. And you got a lot going on in here. And what really happens in some cases is that light you're looking at could be thought to be scattered by this arrow and captured by these lenses and refocused and, cleaned up a little bit and then brought onto this plane. To see in inverse space, we'll construct a scattering instrument. There we did it. We've done it, okay? We first take away all of that optics that we don't need, and then we put in some slits to define a direction for the incident light, and we put in, let's just say, 4 detectors, each of them at different angle, and what we observe is that the intensity goes down with angle, okay? So my lowest angle here is actually this green arrow here. I guess my next lowest one is hard to tell whether it's that green arrow or that one. But the idea is that you have 4 angles, 4 different angles. And in general, the intensity will go down with scattering angle. Now, in fact, it's always going to go down. The question is whether you can see it, whether you can detect it. If it goes down too little, that decrease in intensity gets lost in noise. There's still noise in these experiments. And so, you know, in a perfect world, you would have intensity going down with angle, and you could choose any angles and any wavelengths you wanted. As a matter of fact, we have to actually choose certain angles and certain wavelengths in order for this intensity to go down enough to be seen. Okay, so this is a SAX instrument, and this one is one that we built at LSU. It's been dismantled now and reassembled. It works even better with new cameras and other things on it. I have a picture of that somewhere, but I don't know where you go. The X-rays in this instrument start somewhere off to the right. Don't worry about them. They come out of an X-ray instrument, let's just say that. And they are, you know, there's some slits that give them a defined direction. And they just go shooting down this tube, and they eventually would hit the center of that camera, this square thing at the back here. This is a camera, okay? And it's just a pixel camera, similar to a CCD in concept, but in design, totally different. Well, all the angles, your sample sits up here in this sample chamber, which is usually evacuated. There's a vacuum applied across this whole thing because the X-rays that are used here don't like to penetrate. These are what are called soft X-rays. They don't have enough energy to really penetrate even air over long distances. So these aren't the same X-rays that you use when you get an X-ray at the doctor's office. So anyway, the X-rays come shooting down here. They would go straight through, and in fact, there's a beam stop to prevent the camera from being damaged by them. But then if your sample is here, it will scatter light, and it will scatter it off, look very carefully where I'm pointing, to, let's just say, to the top of the detector or to the bottom of the detector. So there's pretty small angles. You can see that this is a pretty small angle going from here over to there. That's a pretty small angle, a degree, 2 degrees maybe. But anyway, pretty small angle. And that's necessary for these kinds of experiments. We'll talk about why. This is another one of these instruments that's arranged in a straight line with a camera. This is actually a visible light scattering apparatus. Down here is a laser. The sample sits here, and there's a camera up here. Okay. Over here is a sort of a kind of another schematic of it. Now we have one of these, and maybe we'll play with it or not. We'll just see. If you're in the lab, you can ask to play with it. Okay. Another straight line apparatus is built. This is up at Oak Ridge National Lab. There's a picture of a gentleman here doing something with the detector. This is a neutron scattering, and I think at the other end of this one is a nuclear reactor that produces neutrons. The neutrons, they're particles, but we know from de Broglie that particles are also waves, and so they exhibit wave-like character, and they are given a particular wavelength or a particular range of wavelengths. And the scattering sample is over here, and the detector is over here, and again, pretty small angles are involved. Okay, so it turns out that the reason we have to go to these low angles in this case is because we're looking with very short wavelengths. Both X-rays and neutrons have pretty short wavelengths under the conditions that we make them. And it also matters that we're looking for pretty large features. This is not the same kind of problem. Well, it's related, but it's not instrumentally. It's different from normal single crystal X-ray diffraction. Okay, so then there's another kind of instrument, and that's a rotating detector or high angle systems. This is a rotating detector high angle system, and this is a top view of a different kind of system. We own both of these. The top one has, I guess, 16 different detectors arranged in two semicircles to cover an angular range. And this one has only one detector plus Kyle here, and he will rotate that detector from one angle to the next, and you get to see that. All right, so Most of the straight line instruments are used at low scattering angles, and these handle an enormous range of different kinds of samples. Okay, so this is just sort of showing you some of the things that you can go. Sometimes you get structured patterns. Here's one that's structured. Sometimes you just get sort of a random decay. And so either one just sort of reflects what's going on in the sample. All right, so what scattering detects is something like the Fourier transform of an object. So I want to talk a little bit about that. Let's look at some letters here. Fourier transforms are inverse operations. If it's a Fourier transform in time, then short times correspond to high frequencies. If it's a Fourier transform in space, like light scattering, then short distances correspond to high angles, okay? So, or high spatial frequencies, we may say. So look at Z here. Z has 3 horizontal lines, and that they together are producing this vertical streak here, okay? And it has one sort of long diagonal line, and that's what produces this diagonal, but oriented to the side because of the inverse nature. And so you can try to convince yourself that the rest of these make sense. T certainly makes sense. H is looking like T. What's the difference between an H and a T to a Fourier transform, see? So in microscopy or any visible real space method, it's easy to tell H from T. A little more difficult to do it here, okay? If you look carefully, you'll see that the H has a bunch of little bars in there, a bunch of little spots, whereas the T is kind of more continuous. And so you can distinguish, but it's not as easy, and we're just not conditioned to see in that space. This is an unusual one here. This is a Fourier transform of some image, and you'll never guess. So it's a Fourier transform of Mickey Mouse. And he's pretty round. Most of his features are round. And so it's not surprising that most of the features here are round. But the features that appear at high scattering angles would be the smaller details, maybe the eyes and stuff like that here. This was Bob Bacora. I told you we'd have famous scatterbrains throughout history in this talk, and Bob is at Stanford and invented, basically, co-invented, I would say, dynamic light scattering. Certainly put it on a great theoretical foundation, okay? And he told me once that he sees better in inverse space than in real space, and I don't doubt it. Okay, so we're going to do a little exercise here to try to understand Fourier transforms, and I have an application which I hope will run and behave. Let me switch to that and just see what happens. And this is written in something called LabVIEW. I don't know if you can hear that or not, maybe, but it's making sounds. And I can adjust the frequencies. And what I've got here is 2 waves. It's a little hard to see them because their frequencies are high. I guess maybe if I lower the frequencies, we'll see what happens. This is a problem that you have with digital signals, is that they alias to the signal. Okay, so here's, well, let's see if we can maybe get this one down. There we go. So now you can not very clearly see, but you can sort of see that there are 2 waves here. Here, we'll make them. Let's make it, yeah, let's make this one 8. Okay, so anyway, actually make this one 4. Okay, so that's a sine wave on the top, and there's another sine wave on the top, And you can sort of see sub-patterns in here because I don't really have enough pixels on my screen to represent what's going on with this wave very well. And that's called aliasing. But down here you see reasonably well what the sum of the two waves is. And their Fourier transform is crushed over here onto the right side. This is the so-called power spectrum. So I'm going to go back and make these, a little higher, and you won't be able to see what the waves are anymore, but trust me, they're there. Okay, and well, the Fourier transform operation is figuring out, oh, I got two waves here. Moreover, the one at high frequency has greater amplitude. Let's change the high frequency amplitude. Let's reduce that. Oops, I guess I do that here. Let's change it to 0.25 to match the other one. And now you see that they're basically the same height. You really want to integrate underneath those, but they're pretty sharp. And you can see that they're the same. Let's see if we do 0.5 and 0.25. So now I've given the low frequency the greater amplitude. Well, I don't know if you get to hear this or not. I get to hear it, and it's kind of annoying sounds. But, if you can actually hear these differences, and your ear is quite accustomed to doing a Fourier transform. Your brain-ear system is designed to be able to detect high frequencies and distinguish them from low frequencies. And you use this in threat assessment. You use this in what to ignore, what not to ignore. As you get older, as I have, you lose some of that high frequency capability. So it's a little harder to hear sibilants. See, that's a sibilant. And you can probably hear the difference from when I'm talking low like this. And you have no problem with that. A question was asked recently whether this is, why people who shout in low tone may get more attention. I'm sure that we're probably conditioned by either nature or by culture to pay attention to certain frequencies, and that's all I'll say about that. Okay, well, I'll stop this. And I think what I wanted to do, I wanted to show you the language that that's written in, which I have here on the screen. This is the code for what you just saw. And you see that it's not anything about it written. This is a software program called LabVIEW. It's very powerful. It's a little weird. Electrical engineers like it. You can see it's laid out a little bit like a circuit diagram. But when we wanted to make a sine wave, we have some inputs here. We put them into the sine wave thing. And, we did another one, and we actually took a difference, and we actually plot the sum, and you get the power spectrum from the power spectrum icon, and you just basically wire these components together in LabVIEW. It's an interesting language to learn. It's very powerful. All right, let's go back to what we're doing. Okay, so Fourier transform inverts the inverts the features. The small wiggles that you see here are what corresponded to the high frequency, and the overall sort of slow sine wave that's underlying here is that low frequency. Okay, so that's what they do. Now, we're used to hearing like that, and like I said, our ears handle that for us automatically. But it's an interesting question. What happens in other domains? So we're used to that time frequency domain, and that's pretty common for us. And if you're into audio or stereo or any other thing like that, you're quite adept at making those distinctions. But the equation form of it is a little bit messy, but not so bad. And then we're going to talk about what it looks like in another domain. Let's look at these equations served up from Wolfram alpha. Here's a Fourier series that represents a square wave, okay? So the square wave is there in black, and the components that are required to build it are shown in other colors, okay? Actually, I think what they're doing is showing you the sum of these components individually. And it turns out that what you really want is the odd harmonics. So look at the equation here. The function is a sum of the odd harmonics 1, 3, and 5. So we have a basic fundamental wave, maybe 100 hertz. And then we have 3 times that, 300 hertz, 5 times that, 500 hertz, and other. Okay, and so you need, oh, I don't know, 5, 10 of those signals to get a reasonable approximation to the square wave. Okay, now the reason that those high frequencies are required is because there's a sudden step up. If this is a time domain, then we're going along in time, my signal's low, and then boom, over a very short period of time, it jumps up, and then boom, it jumps down over a very short period of time. So because there's a short period of time involved, I need to have high frequencies present in my Fourier series to simulate this wave. For a triangle wave, you can see it's much more gentle. Nothing happens suddenly. There's no boom. It's more like so it's more gentle, okay? So I don't need so much high frequency energy. So how is that accomplished? Well, again, it's the odd harmonics that matter, 1, 3, and 5. But you don't need as many of the high harmonics. So instead of 1 over n here, you have 1 over n squared. So that kills the higher harmonics pretty quickly. Okay? So in static scattering, we're really looking at spatial frequencies. We talk about intensity, I, as a function of this thing called Q, the spatial frequencies, okay? In dynamic scattering, it's that, but we also have time. So we have I of QT. Well, if I have I of Q, there must be some real space thing that I'm going for, some S of X, X being a dimension in space. And in dynamic scattering, if I have I of QT, I really have 2 Fourier transforms. I have the one to deal with the spatial part and one to deal with the frequency part, which turns out to be, in our case, how quickly things are moving. Okay, so I want to talk a little bit about what this Q is, and we'll talk about this for a while. It's really how many tick marks are on your ruler. So here's a ruler, here's, with lots of tick marks on it, okay? And here's another ruler with, a tick mark there, a tick mark there, just one tick mark basically, but we'll say there's another one there, all right? So it's really the resolution that you have. If I'm going to size an object, then I'm going to do that better when I have lots of tick marks, right? If I need to measure the size, pick an object, a pencil. What's the length of the pencil? Okay, I can determine that better if I have a ruler that's lined out in millimeters than I can if I have a ruler that only shows me every centimeter. Okay. Well, okay, returning again to this inverse business, this is a scattering pattern off of a liquid crystal that has a kind of a banded structure in real space. And in scattering space, you see these diffraction patterns. If the banding structure in the top were to anneal and change over time, then in such a way that these lines grew closer, it would make the scattering pattern expand outward, horizontal sense. Okay. Here's another one, block copolymers. This has been a big deal. People have been studying these for a long time. In real space, you sometimes, if you have them, treated them right in your electron microscope, you can see these kind of lamellar looking type structures, bands here everywhere. And in scattering, you sort of see these as wings on the side. So the center thing here is the beam stop. That's where the beam would hit. Usually that would destroy the detector or be overly bright anyway. So that's usually prevented. So what they often do, this is X-ray data, so they probably put a piece of lead right there where my red spot is. And that lead absorbs the main beam, and then the scattering power is seen off to the side. And part of the art of doing these experiments is having just the right size of beam stop so that you can get to lower and lower scattering angles corresponding to longer and longer distance. This is the same thing again on a more modern instrument, and they set it up to do rheology. So one of the things about scattering is that it's a little easier to do rheology while you're doing scattering. You could stretch a sample, you could twist it, you could shear it while you have the sample present. That's a little harder to do in an electron microscope where you have lots of constraints, particularly the thickness of the sample. It has got to be maintained very low for electron microscopes. Okay, so that's actually a pretty good place to stop. I'm going to pick up here in a little bit, but you should at this point take a break and write down some notes and some main features that you saw and send questions or something like that. But at this point, I will stop.